We address the open problem of resolving simultaneous impacts. Drawing motivation from the successes and pitfalls of two popular approaches, we propose a novel generalized reflection model and a complementary generalized restitution model. Existing methods fail to simultaneously fulfill one of three desiderata: breakaway, symmetry preservation, and kinetic energy conservation. Propagation models, such as Gauss-Seidel and Jacobi, capture experimentally validated and expected braking behavior in stiff impact. LCP models, in contrast, artificially constrain objects to remain in contact. Gauss-Seidel models, however, artificially break spatial symmetries when faced with multiple impacts. While LCP and Gauss-Seidel preserve kinetic energy for elastic impacts, the Jacobi model fails in this regard. For these three desiderata, there is no perfect published method. We address this by introducing the generalized reflections impact operator. Our approach amounts to a careful combination of the LCP and Gauss-Seidel formulations, provably fulfilling all outlined desiderata. We inherit the symmetry preservation of LCP, the breaking contact of Gauss-Seidel, and the good kinetic energy behavior of both methods. When a stack of balls is dropped in a container, it should break apart. Unfortunately, LCP introduces an adhesion-like effect, preventing the expected splash. These same sticking artifacts carry into three dimensions, even for non-unit restitution. When we drop nested Matryoshka dolls with LCP, they rebound as a single, solid object. The Gauss-Seidel model suffers from a different set of artifacts, destroying symmetry when faced with multiple constraints. By arranging 8 boxes in a cube configuration, and in turn assigning each box a symmetric outward velocity, nothing in the system should break symmetry. Releasing the cubes in a zero-G environment, generalized reflections remain symmetric, while Gauss-Seidel descends into disorder. The destruction of symmetry can have unintended consequences. This threefold rotationally symmetric trefoil knot should bounce straight up, but Gauss-Seidel induces a tumbling mode after the first impact. In a final test of long-term symmetry preservation, we initialize 2 rigid bunnies with a 180-degree rotational symmetry. The trajectory produced by generalized reflections preserves this symmetry for the duration of the simulation. Repeating this test with friction and non-unit restitution, note the preservation of symmetry. To explore the scaling of our model, we simulate 1 million billiard balls in a grid where neighbors are initially in contact. Assigning each ball a random initial velocity, we capture large-scale symmetries for long run times. To push the scaling behavior further, we simulate the same grid, but instead set all initial velocities to 0 and drop the grid under gravity. Even with the huge number of multiple impacts, we still capture the large-scale symmetries of the system. Finally, for validation, we reproduce the experimentally observed emergent phenomenon of extended patterns. We place 60,000 rigid body spheres in a vibrating container subject to friction and normal restitution. For this particular driving amplitude and frequency, a stable hexagon pattern emerges. We note a match to the experimentally observed pattern on the right. By driving the container at a different amplitude and frequency, the grains form a stable square pattern. Notice how the square pattern emerges dynamically over time and remains stable in correspondence with the experimentally observed behavior. Again, We note a match to the experimentally observed pattern on the right. Finally, by driving the container at yet a third frequency and amplitude, stable stripe patterns emerge. The challenges to simulate these patterns are directly in line with our goals. The generation of stable patterns requires high-speed impacts, accurate and scalable modeling of multiple impact, restitution, and friction.